Welcome to the next video in the group theory series. In this video, we will talk about the order of an element when raised to some positive exponent. You can see here a preview of what we will cover in this video. Now, since we are interested in finding subgroups and the cyclic ones are so nice, we'd like to get as many of them as we can. We can always get a cyclic subgroup by taking any element and looking at the subgroup it generates. What if we take this element and raise it to some power? It's straightforward to prove that this is always a subgroup of what G generates. This is already a nice observation since it helps us to organize the lattice of subgroups of a group sometimes. For instance, consider the dihedral group on 4 vertices, which is D sub 8. You can see its lattice here. If we consider the subgroup generated by R, it consists of 1 R, R squared, R cubed. If you then consider the subgroup generated by R squared, it is the subgroup consisting of just 1 and R squared. And the point here is that this can help you to find subgroups. Once you've found the subgroup generated by R, you can find the subgroups of it by taking exponents and looking at the subgroups generated by them. We can demonstrate this with one more example, Z mod 8. Here, because the group is additive, we will not write exponents. Their equivalent in additive notation is multiples. So of course, the whole group is generated by 1. If we take the multiple of 2, we get a subgroup of that. But to illustrate the point above, we can see that the group generated by 4 is a subgroup of the group generated by 2. And of course, 4 is a multiple of 2. So we could sort of anticipate that they would be subgroups by seeing that 4 is a multiple of 2. Also, by the way, think about the orders involved here. 2 has order 4, you can check it. 4 has order 2, check that. You may want to appreciate right now, as it will become significant in a moment, the various GCDs, right, greatest common divisors, with 8, the order of the group. The GCD of 2 and 8 is 2. And the order of 2 is 4. Okay, the GCD of 4 and 8 is 4, and the order of 4 is 2. So thinking about these relationships of GCDs and orders should hopefully show you a bit of a pattern. Let's make a few more observations. The elements that generate Z mod 8 are 1, 3, 5, and 7. So, take a moment, convince yourself, however you need to, that, of course, Z mod 8 is generated by 1, but it is also generated by 3, right? Do 3 plus 3 enough times, and you'll make a full tour all the way around the group. Likewise with 5 and 7. It cannot be a coincidence that these are the numbers coprime with 8. Coprime means they share no factor other than 1. So maybe just it would be a little bit clearer if we instead think about the numbers that do share a common factor with 8. So certainly 2 and 8 share a common factor of 2. 4 and 8 share a common factor of 4, as well as 2. 6 and 8 share a common factor of 2. And these elements, 2, 4, and 6, do not generate the whole group, But all the coprime numbers, right, all the ones that don't share a factor with 8, again, those are 1, 3, 5, and 7, the remaining numbers, those do generate the group, and that can't be a coincidence. In this video, we will see a theorem which gives some insight into this relationship and some more. As a further warm-up for the main theorem of this video, let's consider what the order of an element is. So we will write the order of little g as n, and we're considering the situation where n is divisible by some positive integer m. Now, by definition of division or divisibility, n equals mk for some positive integer k. And the whole question, right, what we're sort of warming up to is understanding the order of g to the m. Now, clearly, g to the m to the k, right? That's a natural thing to investigate, right? You would maybe guess that this other number k seems like it probably should be interesting, and perhaps is the order of g to the m. Quickly, you find from the exponent laws that at the very least, it clears g to the m, so that makes it a candidate for the order of g to the m. Certainly, we know that the order of g to the m is no more than k. To show the reverse inequality, we will consider this other number L, which clears g to the m. Recall, right, the definition of the order of some element is the least positive integer that clears it. Well, so what we're going to do is, right, to show that k is the order of g to the m, we're going to consider any other positive integer that clears it. And we will argue that k is less than or equal to L. So that's the strategy here. Now, we know from definition of n as the order of g that, well, certainly, right, we already had that n is equal to mk. That was just simply by, in a sense, by definition of k. But also by the fact that n is minimal as a thing that clears g, then, right, we have that ml clears g, and therefore mk less than or equal to ml. And then by canceling m, you get that k is less than or equal to L, precisely as desired. So we now have that k is the order of g to the m. Note, by the way, that k, right, from how we had it earlier, k just is the same thing as n divided by m. So we now have that the order of g to the m is n divided by m, which is certainly consistent with some of the observations we were making earlier. Anyway, we would like to now try to extend this understanding to the case when m may not divide n. And so in that case, what is the order of g to the m? Well, maybe let's look at a few sort of demonstrations. So let's look this time at z mod 10. Now, certainly the order of 1 is 10, right, as always. The order of 2 is 5. Now, that's kind of very much like what we were already seeing with z mod 8. And the order of 3 is back to 10, again, right, very consistent with some of our earlier observations. So the idea seems to be, so by looking at these examples, you might guess that perhaps the GCD has something to do with this, right? If you take the entire group's order, 10, compute its GCD. Now, in the case of 2, the GCD of 2 and 10 is 2. And then if you take 10 divided by 2, you get the order of 2, right? If you do this all over again with 3, you'd find that the GCD for 10 and 3 is 1. And so the order of 3 is 10 over 1, which is 10. So, right, so what we seem to be perhaps noticing is that the order of g to the m seems to be n over the GCD. Now with that suspicion, let's go ahead and try to do a proof. Now to prove this fact about order, then naturally we're going to want to take our element g to the m, raise it to the power of n over GCD, right? And the natural thing to do is to try to kind of like, use our exponent laws, put those exponents together, then sort of rearrange and leave the n on the inside and everything else outside of that because, well, we know that g to the n turns into the identity, right? That's what makes all of this a fairly sensible sequence of steps. You do have to be a little bit careful, especially in this setting, with doing those steps because division introduces a certain concern that some of these things may not be integers. You could kind of confirm that sometimes, like if you take g to the 2 to the 3 over 3, right? Uh, this is all integers, right? 2 is an integer, 3 over 3 is an integer. You could put these together using the exponent laws, rearrange, regroup, and pull the 2/3 part out, and you're no longer dealing with an integer, and this is not defined. So this would be an invalid proof if we were at some risk of this kind of thing happening. But it turns out that more or less due to some basic number theory. If you have the GCD of n and m, I mean, really, this is even just from the definition of GCD, that it divides both n and m, therefore both quotients turn out to be integers, and therefore all of these maneuvers are valid. So this is a valid proof. You just want to make sure that you really understand why each of these moves were valid, even though division was playing a role here. So anyway, now that we've done that much of the proof, we have this result. The order of g to the m is no more than this number, and now we need to show the reverse. Now, in order to prove the reverse, we will prove that in fact divisibility holds, which might be a little bit surprising because after all, divisibility is a stronger result than merely being less than or equal to. And you might think, well, why would we prove a stronger result? Aren't those usually harder? And we don't need something, right? We don't need all of that for our current purposes. And so, right, that's fairly reasonable, but sometimes concepts just go together, right? So if you were trying to prove this in the wild, right, or maybe you have some other problem in the future which involves the GCD and you're trying to, prove an inequality, you might want to try to prove divisibility in general because, well, the GCD is defined in terms of the concept of divisibility. So it makes it a bit of a more natural match. And, in this particular problem, if you did try to prove it directly without using divisibility, you might find that it's quite hard. So anyway, so it is a sensible move to make to try to prove divisibility rather than mere less than or equal to. Notice, by the way, that by very elementary sort of manipulations, proving this thing is the same as proving this other thing. So we're going to show that n divides the GCD times the order of g to the m. Now, again, right, as a note on strategy for these sorts of proofs, often the GCD is not the best thing to work with directly because it is merely the minimum over, a set, the maximum over a set of common divisors, which doesn't tell you a ton about the properties of that number. So it can be hard to use in proofs, not always. This is a rule of thumb, of course. But often Bazow's identity is a much more usable thing, especially for algebraic manipulations, because you actually get a number, right? So what does Bazow's identity tell you, right? Bazow's identity says that if you, ever have two integers, in our case, m and n, then there always exists an integer linear combination which accomplishes the GCD, right? So that's this, right? This is an integer linear combination because all of the quantities involved are integers. It is linear because we're merely uh, using plus and times, basically. And it's a combination because we're doing times and plus, right? So we're combining these quantities. So this is an integer linear combination, and it accomplishes the GCD, right? So Bazow's identity, a fact best proved perhaps in a number theory course. Uh, although if you want to see a proof of it or some discussion of that, then let me know, leave a comment. But in any case, that's Bazow's identity, and it's often right whenever you're dealing with the GCD, it's often best to use Bazow's identity. It can help a lot. So that's what we're going to do. So we're going to let x and y be these two integers, which satisfy Bazow's identity. So now for us, we can simply replace the GCD where we used to have the order of g to the m times the GCD. We can replace the GCD with this integer linear combination. We can distribute. And this part of it, right, this part right here, already has n in it. So n certainly divides that part. If we want to show that n divides the sum, it then suffices to prove that n divides the remaining part. And so that's precisely what we're going to do. Now, you might think that that's actually a little hard, right? It's a little not immediately opaque how we're going to prove this divisibility relationship, but there is in fact a sensible move that if you spend enough time thinking about it, you'd come up with, which is, well, look, one of our most frequently used divisibility results so far has been this whole idea that if an integer clears a group element, then the order divides the integer. That's exactly what we'll use here, right? N just is the order of G. So really, right, if we're going to use this result, what we want to do is show that this integer clears G, right? Then we'll have this divisibility result. So we're going to try to show that order of g to the m times y. We're trying to show that that number clears g. Now, when you're staring at that, you think, well, how am I going to show that this comes out equal to the identity? Well, one thing that you kind of notice is that you've got a g to the m here, and also here you've got a g and an m. So maybe putting them together in some kind of productive way will get you the result that you want. Indeed, using your exponent laws, you regroup like that, and it turns into the identity, and that sort of just knocks over the last domino that was set up. And so from here, looking back over everything else that we had already set up, they're all right. All of the things that we said that we need, we now have. Okay, next, right, the rest of that was the main result of this video. For the remainder of this video, we're simply going to prove some slightly simpler theorems that are thematically related. So to get started with, we will show that every subgroup of a cyclic group is cyclic and in fact generated by the exponent of g, right? If little g is the generator of our cyclic group, then this subgroup is generated by the least exponent of g that is contained within H. Now, I think it makes some intuitive sense that it would be the g to the I for a minimal choice of I, or as I've written it here, g to the d, where d is minimal, but anyway. Certainly that's an element of H, right, and just by definition. And I also feel, right, I'm just talking feelings for a minute, but that just feels like what should generate H, because if you had something that it didn't generate, then just you might have a rough instinct that then you could compute the division between them, right? Take one divided by the other, get a smaller element, which would contradict the idea that D was chosen minimally. And, not sure if anybody else shares this instinct, but one way or the other, we're going to turn this basic idea into a rigorous argument. So to show that H is in fact generated by G to the D, with D defined in this way, we're going to do a mutual inclusion argument. Now, one direction of the inclusion is pretty immediate, right? H being a subgroup, it is therefore closed under all of its products, and since it contains G to the D, then everything G to the D generates, being products with itself some number of times, they all have to stay inside of H, right? So the group generated by G to the D must be contained within H. The real question is, how do we know that everything in H is one of those? So for the reverse inclusion, let's start by taking an element out of H, call it little h. Now, G, as we said, is cyclic and generated by little g. So it must equal some exponent of little g, right? Call it I the exponent, such that G to the I is H. Now, we can go ahead, right, as we've done many times in somewhat similar circumstances. We can go ahead and apply the division algorithm to get a quotient and remainder for, right, applying this to I and D. And from here, okay, that of course tells us that H is G to the DQ plus R. We could sort of like use our exponent laws to split and rearrange some of this stuff. What are we going to then do with that? Well, certainly the part that is about G to the D, right? We could get that, and that seems like that must be relevant. Well, okay, what do we know about anything relevant to that? Well, since G to the D is in H, also G to the DQ is also in H by a fairly simple exercise with exponent laws. And then its inverse, G to the negative DQ, is also in H, and that gives us the power to take this G to the I, which is to say the same thing as G to the DQ plus R. We can take that and take its product with G to the minus DQ. That's a product of two elements in H and therefore is in H, but it simplifies down to just G to the R. So, kind of high-level summary of everything that just happened here is that we just found that any H, any little h in big H, can be written as G to the R, where effectively R is that I mod D, basically, right? That's kind of what this is, right? R is I mod D. So our H being G to the I, or sorry, the G to the I mod D is in H at least, right? We know that fact. We know that G to the I mod D is in H. And then what we know is that, well, by the minimality that we imposed on D, and R is, some number less than D, but also D was defined to be the least positive integer, such that G to the D is in H. Well, that pretty right leaves only one option for R, right? It can't then be a positive integer, right? Since we know that it's less than D and at least 0, can't be a positive integer, so it must be 0. So we just proved that, in fact, H, right, we can drop the 0 from earlier, or drop the R from earlier, and write this as just G to the D to the Q, but then that is in the group generated by G to the D. right? It's an exponent of g to the d, and so by definition in the subgroup generated by g to the d. So that concludes the proof, QED. Okay, on to the next theorem. So in this one, we will show that effectively, if for a finite order element, uh, some number divides the order, some d divides the order, if and only if there is a unique subgroup of that order d, of order d. Okay, so let's start the proof by assuming that d divides n. Okay. Immediately by definition, there exists this integer k such that dk is n. I think it is a fairly reasonable thing to start investigating whether or not g to the k will get us, right, the subgroup generated by g to the k will be the subgroup that we are trying to find. It will be if it has the right order, right, if it has order d, and of course, we know immediately from this, we know immediately from the main result of this video that its order is n over GCD GCD is just equal to k. So we get n over k, which is from the definition of k equal to d. So that furnishes the subgroup that we were interested in, the subgroup of order d. Now, to establish uniqueness, we can refer to the previous two arguments or results. I'm not going to do all the details. It would be a good exercise for the viewer to fill in the details, but here's the rough, quick version of it. Take any other subgroup which has the same order as this subgroup that we've already found, the one generated by g to the k. Now, this other subgroup, it must be cyclic because all of this is taking place inside of a cyclic group. Any subgroup of the cyclic group is cyclic. We know that this other group must therefore be generated by some g to the d, where d is the minimal exponent of g, which is contained within h. Now, apply the main result of this whole video to argue that that g to the d is the same as this g to the k by basically just looking at these equations for their orders and the order of the group and so on. Anyway, that's the short version of the argument. Okay, so let's take that to prove that the subgroup is uniquely determined. Now we'll do the converse. So for the converse, we're going to take any subgroup of our cyclic group generated by G. This subgroup is cyclic. It must be generated by g to the x, where x is chosen minimally inside of h. And now let's look at the order of h, which is the same thing as the order of this element, the generator. We know that the order of h, by assumption, is d, right? That's what we were assuming from the very start. But we also know that that is equal to n over GCD of n and x, right? That's the main result of this video. And then by sort of like rearranging, by rearranging this equation, then we have that d divides n, and we're done, QED. It's worth emphasizing that the results that we found here for cyclic groups do not extend to all groups. So the uniqueness condition can fail for some groups. This is a really easy one to point to, Z mod 2 cross Z mod 2. That has 3 subgroups of order 2, and you're encouraged to find them all. But so uniqueness can fail, right? Just because 2 divides the order of the group doesn't mean there's a unique subgroup of order 2. But it can fail even worse, right? Sometimes there's simply no order or subgroup of that order, right? So 15 divides the order of S5. Recall S5 is the group of permutations of 5 elements. It has order 5 factorial. Definitely that has a factor of 3 and a factor of 5. So 15 divides that order. And yet there is no subgroup of order 15. Showing you that there's no subgroup of order 15 kind of involves showing you all of the subgroups, or at least that would be the most straightforward way to do it. That would take a very long time. So I'm not going to, but certainly, any viewer who is sufficiently passionate can do it for themselves. But I claim that is a counterexample, right? Where the number divides the order, but there is no subgroup of that number, of order that number. Anyway, however, there is one part of this, one piece of this, that does generalize to arbitrary groups, and that is the fact that if you have any subgroup, its order must divide the order of the group. And this will be an important result, right? And this is one of the main results of all of group theory, basic group theory. And so that is true, and it is very important, but we won't be able to prove it until a few videos from now.